We continue with our series of lectures on local deformation and rotation rates. So in this third lecture, I will be talking about expression for shear deformation rates in two dimensions. Then we will have a look at physical meaning of velocity partial derivatives. Can we extract some physical meaning from the ideas of local deformation and rotation rates that we have discussed? Then we will move on to examining some very peculiar and interesting properties of strain rates and rotation rates, again in dimensions, and we will end this third lecture by extending the ideas that we have evolved in two dimensions onto the three-dimensional flow fields. Right, so we pick up the discussion on shear strain rate at a point in two dimensions. So as I pointed out earlier, for shear strain rate you need to consider a pair of perpendicular material lines, of course infinitesimal. Now, while it's not necessary to choose perpendicular material lines, in fact they can be chosen at any angle and we can talk of shear strain rate, but for the sake of a uniqueness in our, you can say, in the area of fluid mechanics, so that everyone who is working in fluid mechanics works with the same convention, so to speak. So we would like to evolve a definition which is considered sort of universal. Okay, so we fix up a convention, that would be the right word, by considering only pair of perpendicular material lines, infinitesimal, AB and AC, as the figure shows, and the orientation of this pair we can choose at any angle. We are free to choose the angle, so that is shown as theta with respect to the x direction. Now the instantaneous rotation rate of the two material lines, infinitesimal material lines, AB and AC, you can use it to determine the shear angular deformation rate at point A. So it's not, it's very obvious that the rate of change of angle between two initially perpendicular material lines, AB and AC, that rate of change of angle will be simply equal to the difference of the angular velocities omega AB minus omega AC, and I've written clearly that this choice omega AB minus omega AC, this is not unique in the sense that we can also write the shear strain as omega AC minus omega AB. So, I mean, whether you choose to subtract omega AC from omega AB or omega AB from omega AC, both ways the shear strain rate can be defined. But again, for the sake of uniqueness in the subject, so that everybody follows the same rule and convention and there are no confusions, so we fix up again a sign convention for the shear strain rate. And what is this sign convention? The sign convention says that the reduction in the angle, that is, initially if you choose the material lines as perpendicular, then the reduction in the angle gives rise to a positive shear strain rate. So if there is a tendency of reducing the angle, then we should get positive values of the shear strain rate. So if this sign convention is fixed, then the shear strain rate logically must be defined as omega AB minus omega AC, because if omega AB is more than omega AC, then this would have the effect of reducing the angle between two initially perpendicular material lines. Okay, so now again some symbolic convenience. Gamma AB comma AC is more conveniently written as gamma theta comma theta plus pi by 2, because after all the AB AC mutually perpendicular infinitesimal material lines, they are characterized by their orientations with respect to the x direction. So AB has the orientation theta and AC has the orientation theta plus pi by 2. So I can write the shear strain gamma theta comma theta plus pi by 2 as omega theta minus omega theta plus pi by 2. Now it only remains to use the expression for omega theta that we have earlier derived in the lecture 2. So I simply use those expressions for omega theta, and I can also obtain the expression for omega theta plus pi by 2 by simply substituting for theta as theta plus pi by 2. So if you perform the algebra and simplify, you get a final neat looking expression for shear strain rate between any pair of infinitesimal material lines that are initially perpendicular and oriented at some angle theta with respect to the x direction, and this shear strain rate is given the notation gamma theta comma theta plus pi by 2, and this is equal to this expression on the right. So del v del x plus del u del y multiplied by cos 2 theta, and del v del y minus del u del x multiplied by sin 2 theta. So again we see that it's a periodic function because of the cos 2 theta and sin 2 theta terms, and the period is again pi, as was the case with the epsilon theta, the longitudinal strain rate and rotation rate. So now we can continue on the right, the discussion that is given on the right side of the slide. The expressions for these three quantities that are now with us, epsilon theta, omega theta and gamma theta, they will allow us to physically interpret the partial derivatives of the velocity components, the four partial derivatives that are appearing in these expressions. Now, to put it simply, if you consider epsilon for theta is equal to 0, that means you have a material infinitesimal material line at some point in the flow domain which has an angle of 0, means it's aligned along the x direction. And suppose you also consider another material line which is having theta is equal to pi by 2, which means it is aligned initially, the infinitesimal material line is aligned initially with the y direction. So if you consider the expressions of epsilon theta and you substitute theta 0 and pi by 2 in those expressions, we will have the following interesting result, that epsilon theta 0 will come out to be del u del x, which we will denote a special symbol to that, which is epsilon xx. So I'll explain what this double xx means, and similarly epsilon theta is equal to pi by 2 is equal to del v del y, which we again give a special symbol epsilon yy. Now what is this double subscript notation xx or yy? We simply state it like this, that after all the meaning of del u del x is that it is the instantaneous longitudinal strain rate of a infinitesimal material line, and the strain is along x direction and the line is initially also in the x direction. So there are two x directions involved, the direction of the strain, the longitudinal strain direction, which is x, and the orientation of the material line, which is also x. So that's why del u del x is given a special symbol epsilon xx. And similarly, you can interpret in the same way epsilon yy. So these are the two physical meanings for the partial derivatives del u del x and del v del y. Now to get the meaning of partial derivatives of del v del x, del u del y, you have to go into the expression for the instantaneous rotation rates. So again, if you consider infinitesimal material line which is along x, you get its rotation rate as del v del x. And if you consider a material line, infinitesimal material line along y, then you get its instantaneous rotation rate as minus del u del y at a given point in the two-dimensional flow field. So you have the physical meanings now of all the four, you can say, derivatives: del u del x, del u del y, del v del x, del v del y. So it was not really very difficult to arrive at the physical meanings, and rather it is actually looking very simple once the material line strain rates and rotation rates have been, you can say, developed. The concepts and expressions have been developed. Now let us now see what we can do with the shear strain rate. Here also, if we choose the pair of instantaneous pair of mutually perpendicular infinitesimal material lines, one along x direction, one along y, so we will call the shear strain rate associated with them as gamma 0 comma pi by 2. So if we put theta 0 in the shear expression that is on my left, then putting theta 0 simply gives me gamma 0 pi by 2 as del v del x plus del u del y. And this combination of the two derivatives of del v del x and plus del u del y, that means it's a special combination, del v del x and del u del y, when they are added, it gives you the shear strain rate, instantaneous shear strain rates between a pair of mutually perpendicular infinitesimal material lines, one directed along x and the other directed along y. So the appropriate choice of symbol is gamma xy for this quantity. So that's why this quantity is given a special symbol gamma xy, reminding you of the orientation of the pair of perpendicular infinitesimal material lines along x and y. So we now have a physical meaning of the partial derivatives of velocity components in 2D. Okay, this second objective is over now. Now I can just to help you out, how do you write the physical meanings? We can just look at del u del x. you can say that del u del x is a longitudinal instantaneous strain rate of an infinitesimal material line anchored at the point under consideration, aligned along x direction. So I repeat, del u del x is longitudinal instantaneous strain rate of an infinitesimal material line which is anchored at the point under consideration. That means the point where you are finding this partial derivative. And the line, the infinitesimal material line, is aligned along the x direction. Okay, so this gives a longitudinal strain for the infinitesimal material line which is aligned along x direction at a certain point. So now we move on in the same manner onto the other derivatives. So in the same way we can write the physical meaning of the combination del v del x plus del u del y as it is the instantaneous shear strain rate between mutually perpendicular infinitesimal material lines directed along x and y directions and anchored at the point under consideration. So in the same way, del v del y can also be written. I have deliberately not written it here. You can fill it yourself, the physical meaning of del v del y. So this is left as a exercise for the students. Similarly, the physical meaning of del v del x and del u del y can also be written using the fact that omega theta 0 is del v del y and omega theta is equal to pi by 2 is minus del u del y. So you can write in your own words the physical meaning of these partial derivatives. So now coming to the third learning objective of my lecture 3, as I mentioned, there are some very interesting properties, mathematical properties you can say, exhibited by local deformation and rotation rates. And of course I'm talking, restricting myself to 2 dimensions. So the first property that I will draw your attention to is the maximum minimum values. See, because we know that epsilon theta, omega theta and gamma, theta comma theta pi by 2, so longitudinal strain, rotation rates of a single infinitesimal material line and the shear, instantaneous shear strain rate between a pair of mutually perpendicular infinitesimal material lines. All these are periodic functions of theta. So if they are periodic, they will exhibit maximum and minimum values at a given point and a given time instant in the flow domain. So each point at a given time instant in the flow domain will be associated with certain maximum minimum longitudinal strains, maximum minimum rotation rates and maximum minimum shear strain rates. Of course, they will be associated with the infinitesimal material lines, but there will be some material lines, in order to say it in another words, there will be some material lines that will have the maximum longitudinal strain rate, some will have a minimum, another one will have a minimum longitudinal strain rate. In the same way, a particular material line will have the highest rotation rate, and while another material line will have the lowest or the minimum rotation rate, and so on. So let's try to demonstrate what we have just pointed out. For example, if I consider the expression for longitudinal strain rate of a single infinitesimal material line inclined at an angle theta, then the expression is I've already discussed in my earlier lecture. So this expression can be conveniently, as I said, written in terms of the double angle 2 theta by doing the trigonometric manipulations. Cos square theta, sin square theta, and sin theta, cos theta, they can always be expressed in terms of cos 2 theta, sin 2 theta, and so what we have the final expression as it is written in terms of sin 2 theta and cos 2 theta. Now, if you recognize this expression, if you consider this expression as a function of theta at a given point and at a given time instant, the other partial derivatives and all, they will be just fixed numbers, so to speak, and so you can regard this expression as a function of theta alone, how the longitudinal strain rate at a given point and a given time instant would be varying if I vary theta. So it is very easy to write the maximum minimum values without even going into the calculus ways, you can say, because I know that if there is a trigonometric expression of the type a sin 2 theta plus b cos 2 theta plus c, then its maximum value is c plus square root a square plus b square. So as you can see, the maximum value will be this, what I have written here. By the way, the last term is written below. It is basically inside the square root radical sign. Okay, so we will move on with this discussion. Right, the minimum value for the longitudinal strain rate rather, will be then half of del u del x plus del v del y minus the sign in between will become minus now for the minimum value, minus half of square root of this term that I have written here. So the maximum minimum values are very easily written because of the nature of the expression. Then of course we have not used the methods of calculus for finding the maximum minima, so that's why it remains to see at what angles these maximum and minimum values will be found. So these instantaneous maximum minimum values at a point in the flow domain are called principal strain rates. Okay, you might have learnt in some earlier courses in solid mechanics principal stresses and maybe even principal strains. So since in solids we talk about strains, here the strains are replaced by strain rates. So but analogously the maximum minimum values that I have just written, they are nothing but the principal strain rates. Okay, so these maximum minimum values are called by this formal name. Now the corresponding principal directions, so as I mentioned earlier that at what values of theta these maximum and minimum values will occur. So the corresponding principal directions or values of theta, they can be now found if you use the methods of calculus for finding the maxima minima of a function. So what you do, you differentiate the function and equate the derivative to 0. That gives you local maxima minima points. So if you do that for the longitudinal strain rate expression, we will simply get the principal directions given by the angle theta p as tan 2 theta p is equal to del u del y plus del V del x divided by del U del x minus del V del y. So it is this ratio of these two combinations of the velocity partial derivatives that gives you the principal strain rate directions. Now you will notice that because of the fact that tan function is a periodic function with pi, so therefore there will be two values of theta p that will satisfy this trigonometric equation. So now if I denote one value as theta p, the other value will be separated by theta p, separated from theta p by an angle pi by 2, because remember the expression is tan 2 theta p. So if I take one value as theta p, it will satisfy the expression, and if I take another value theta p plus pi by 2, then it will again satisfy the same equation because tan is a function which has a period pi. So I hope this is very clear now. Now, as a small exercise, since I am not doing this in my lecture, you are expected to now take over from this point onwards, and you can do a learning exercise where you analyze omega theta and the shear gamma theta, theta plus pi by 2 for their maximum minimum values. So the maximum minimum values for these two quantities, the rotation rate of an infinitesimal material line omega theta and the shear between two infinitesimal mutually perpendicular material lines oriented at theta. So you can do it yourself and arrive at results for maximum minimum values. You can also find out the corresponding directions which experience these minimum and maximum values. So it's an exercise for you to do on your own. Okay, if you have any problem, if you face any problem or any kind of difficulty, then you can always post it in the classroom, and we will of course answer that query. Okay, so this is one property related to maximum and minimum values. The second, again, very peculiar and interesting property of these local deformation rates and rotation rates is what we call as invariance with respect to theta. So there are certain quantities, certain combinations of these local deformation rates and rotation rates which seem to be behaving independent of theta. That means even if I change theta, these quantities do not change. So what are these? Let us examine. Okay. Now suppose we start examining quantities like epsilon theta plus pi by 2. What do we mean? We are basically adding longitudinal strains of any two mutually perpendicular infinitesimal material lines at a given point at a certain instant of time. Because I am taking one at theta, one material line, infinitesimal line at theta, and the other at theta plus pi by 2, it means that epsilon theta plus pi by 2 is exactly the sum of longitudinal strains of any pair of two mutually perpendicular infinitesimal material lines. So now if you use the expression for epsilon theta and again you add, the sum comes out to be del u del x plus del v del y. This is different from shear. Okay, gamma xy was del v del x plus del u del y, whereas this comes out as del u del x plus del v del y. So epsilon theta plus pi by 2 is del u del x plus del v del y. Now this result is, notice that, is independent of theta, which means it doesn't contain any term involving theta. So it means that physically that whatever pair you choose, the pair must be mutually perpendicular of infinitesimal material lines, but it may be oriented at any angle. Okay, so that means I can rotate my mutually perpendicular pair at a given point and at a certain instant of time. I can just take any pair, any mutually perpendicular pair, because when it is independent of theta, it means that you can choose any mutually perpendicular pair. So if you choose any mutually perpendicular infinitesimal material line pair at a certain point and a certain instant of time, then their longitudinal strain, instantaneous strains, will add up to be the same value. Okay, they will add up to be the same value. So this is something very interesting. This is what we call as an invariant quantity with respect to theta. Now we will later on show that this quantity del u del x plus del v del y represents a very important property of fluid particles, which you will see in the next lecture. Okay. Now we will discuss another invariant, and this time we will use the instantaneous rotation rate, omega theta. So omega theta plus pi by 2, it comes out as del v del x minus del u del y. Again we observe that the result is independent of theta. So the quantity del v del x minus del u del y is independent of theta. So again, if you take any infinitesimal mutually perpendicular pair of material lines at any point in the flow field at a certain instant of time, then you will find that this quantity del v del x minus del u del y will come out to be same for any pair. Okay, any pair of infinitesimal mutually perpendicular material lines will give you the same value of omega theta plus pi by 2. So this quantity, which is invariant and doesn't change with theta, or the pair of infinitesimal mutually perpendicular material lines, we call this quantity as vorticity. Okay, so vorticity you might have heard in your earlier course also, but exactly physically what does it represent in the flow field? This is very precise, you can say, meaning of vorticity, very unambiguous and very clear. So the quantity, the invariant quantity, omega theta plus pi by 2, this is what is known as vorticity, and its value is del v del x minus del u del y. Okay, of course this is all within the framework of two-dimensional flows. We will see later on, when we will towards the end, we will move on to the last objective, where we will extend whatever we have learned to 3 dimensions. There we will see how we can talk of the vorticity there in 3 dimensions. Right, so to complete or to conclude the third lecture, I shift my attention to my last learning objective, which is directly extending the ideas of local deformation and rotation rates to 3-dimensional flow fields. Okay, because the physical conception is already there from the 2-dimensional flow field analysis for local deformation rates and rotation rates. So it's not very difficult to directly extend it to 3D. Let me tell you at this point that it's certainly possible, for those who may be wondering that why we, from the first principles, why didn't we develop the local deformation and rotation rates for three-dimensional flow fields. Well, there are definite reasons for not doing it this way, because if you want to develop local deformation rate and rotation rates by considering a material line, infinitesimal material line in a three-dimensional flow field, the mathematics tends to be very, very involved and complex in comparison to 2D. That is because in a three dimension, a infinitesimal material line will be characterized by not a single angle theta, but in fact minimum two angles in space. Okay, so you need minimum two angles in space to orient a line with respect to the coordinate directions. So this is one of the complications. And then the rotation rates, so in general the rotation of a material line in space will have so to speak two angular velocities. So again the rotation is getting complex in 3 dimensions. So while it's possible, I'm not saying that it's not possible to do it from first principles in 3D, but it serves little purpose in the sense that for students who are going through this exercise for the first time, it's rather more easy to first understand it in 2 dimensions, derive things in 2 dimensions, understand the concepts, and then to simply extend them to 3D. So that's why we are using this approach. Okay, so now as we have seen that if you in 2 dimensions, if you take a very tiny small infinitesimal material line oriented at a certain angle with respect to the coordinate direction x, then you can express its longitudinal strain rate and its rotation rate in terms of 3 quantities: the epsilon xx, which is del u del x, epsilon yy, del v del y, and the shear strain rate gamma xy, instantaneous shear strain rate gamma xy, del v del x plus del u del y. You can go back and just look at the expressions and see what I'm pointing out here. So epsilon theta is completely fixed by once these epsilon xx, epsilon yy, and gamma xy is known, because then the only thing it remains to specify is theta, which is of course a free you can say parameter, and you can fix any angle of theta. So in the same way, when you go into the 3-dimensional world, we can show, as I said, but it is outside the scope of our course here, but we can show that if you consider an infinitesimal material line in space, which is characterized by 2 angles, then its longitudinal strain rate and they can be just expressed by the 6 quantities which I have written here: epsilon xx, epsilon yy, and epsilon zz. So their physical meanings are the same. Epsilon xx means it is the longitudinal strain rate in x direction of a material line along x. Similarly, epsilon yy, longitudinal strain rate in y direction for a material line that is directed along y. So we extend it by saying that the third quantity must be epsilon zz, and that should be the strain, longitudinal strain in z direction in the material line that is aligned along z direction. And its value, if you notice, by analogy, its value should be del W del Z. W is the Z component of velocity. So these are the three longitudinal strain rates that must be employed to characterize the strain rate of an infinitesimal material line oriented in any direction in space in 3 dimensions. And together with these three longitudinal strain rates, we must have three shear deformation rates. Why three? Because one will be due to the material line pair along x and y, that is gamma xy. Then one should be associated with the infinitesimal material line pair directed along y and z directions, which we call as gamma yz, and by you can say comparing with gamma xy, the expression should be gamma yz should be del w del y plus del v del z. The velocity derivatives are you can say crossed, which means gamma yz. So gamma yz means I should be using velocity components along y and z, so v and w, and they should be involved in cross differentiation. So v with respect to z and w with respect to y. So the other remaining shear should be shear strain rate that characterizes the longitudinal strain in any material line in 3D. That should be gamma xz, and its expression is it is the shear strain rate, instantaneous shear strain rate between pair of perpendicular infinitesimal material lines directed along x and z directions. So because in 3D you can have three such pairs, so one along xy and then yz and xz, so that's why we are having three shear deformation rates, and gamma xz can be just expressed as del u del z plus del w del x. So again the two velocities along x and z directions involved in crossed differentiation, you can say. So these are the six relevant you can say local deformation rates, three longitudinal, three shear, that will allow us to express the longitudinal strain rate in any infinitesimal material line located in the three-dimensional space anchored at point A. So next we move on to the vorticity components. So now in 3 dimensions, as I said, in 2 dimensions we had just one vorticity component, which was omega theta plus pi by 2, and that for 2 dimensions that rotation vector is directed normal to the xy plane, so that's why we call it as omega z, capital omega z rather. So capital omega z, this is the invariant omega theta plus pi by 2 associated with the, of course, pair of perpendicular material lines in xy plane. So you will have two such additional numbers in 3 dimensions. One will be contributed by a pair of perpendicular material lines in yz plane, and this will be known as the x component of vorticity. It will be written as del w del y minus del v del z, and you will have another contribution by a pair of perpendicular material lines, infinitesimal material lines in xz plane, and this pair would be contributing the y component of vorticity, and which is written as del u del z minus del w del x. All these three are basically the invariants omega theta and plus omega theta plus pi by 2, but they are contributed by the perpendicular pair of infinitesimal material lines in different planes, x, y, y, z and x, z planes. Okay, so this is how the vorticity components in 3 dimensions look like. So I end this third lecture right at this point. So we have come to a definite stage now after this third lecture. And what is that stage? We have developed local deformation and rotation rate concepts, of course associated with the infinitesimal material lines in the flow field, and we have taken it right starting with 2-dimensional flow domains and extending them to 3 dimensions. Now what I would like to point out as a hint, whatever we have done is done with a very specific coordinate system in mind, which is the Cartesian coordinate system. So every kind of relation that we have is applicable for a Cartesian coordinate system, and but it's not so that only Cartesian coordinate system will be the best and the most suited coordinate system for solving any kind of flow problem. So in fact we will be using both Cartesian coordinate systems as well as cylindrical coordinate systems, which are basically r theta z coordinate systems. So next we will try to tell you how to deal with the various expressions that we are developing for fluid flows, how to deal with them in different coordinate systems. That is what I am trying to hint at is, can we write these expressions that we are developing without you can say attaching ourselves to any specific coordinate system. That means can we write these vorticity components, these strain rate components in a manner which can be recognized as a coordinate free manner of writing the expressions, or simply coordinate free forms of these expressions, so that whichever coordinate system we find we choose to work with, we can readily use this coordinate free expression and then arrive at our expressions for the particular choice of the coordinate system. तो चाहे हम सिलिंड्रिकल में काम करें या कार्टेशियन में काम करें, हमारे एक्सप्रेशंस जो हैं वेरियस फ्लूइड मैकेनिक्स क्वांटिटीज़ के, वो इस तरह से लिखे हुए होने चाहिए. दे शुड बी रिटन इन अ मैनर so that we are not tied down to a particular coordinate system. So what I will choose to do since I have in my 3 lectures covered certain portion of the syllabus dealing with local deformation rates and rotation rates, I'll try to give you a short lecture on vectors and vector functions and tensor functions, and how to deal with them in a general way and in any kind of coordinate system. So that will help you, so to speak, in tackling all these fluid flow analysis situations in any coordinate system. So that will be that is just a window where I'm trying to show you about things to come in future. So thank you very much for this third lecture.